Hello everyone, this is Mohammed from Curtin University. This is me showcasing my assignment for CMPE 4001, the CPU and GPU architecture. So to begin with, we're gonna go to the project repository that I've made. So my project repository is pretty simple. So the way I've made this is I didn't want to use any Quartus because Quartus is I felt is pretty slow, especially how the version of Quartus is a 32-bit 32-bit application, and it just is just really slow. So instead, what I've decided to do is use the Quartus binaries and make my own makefile, and you have a fully integrated terminal experience into making this assignment. Now, to begin with the actual project, um, so you're going to see the config, the source, and the TB. Those are three main important ones. The constraints folder is like a template that I've made a while back when I first learned Verilog, and generated is whatever the binary generates as the output. So that would be my RTLs, my schematics, all of that. And also my simulation and test benches. So first let's go to the toolset that I've made. So if I go make info, it would tell me what files I have, which is quite a bit, and the system that I'm building on, the what hardware description language I'm using, with the what's called which family, which version of software, the actual chip that I'm using. So I'm not using the DE10 Lite. I'm using my own FPGA. It's the EPC2C5, which it looks like this. I'll bring it in. All right. So basically, yeah, this is my power port. They have my left and right were JTAG connectors. These are what's being used to actually program the FPGA. The one on the right is a temporary program, so it's on volatile. It doesn't actually save to the actual chip, and the left one does. It has 144 pins, 3 LEDs and a button. The 3 LEDs and the button are inverse logic, so they're always one until they are activated, which is a 0. That took me a while to figure out when actually connecting everything up. When I scroll down, it tells you like all the tools that I've used, what they mean. So like so they make syntax, just checks the syntax of my source files, actually simulates my whole project based on the test benches that I've created. Synthesize is where it actually uses the tools and converts my HDL language to the intermediary language, or like encoding, or whatever you'd want to call it. PNR is the place and route. This takes in the board information and tries to fit my design onto the board the best it can. Program just makes the actual bit stream of it. I have a couple different open source ones, like OpenFPGA and Native. Those are just different ways of programming it. The list of boards that I can actually program using this script that I made, and there's bitstream, and there's also programs. So bitstream creates the binary that the JTAG or the USB uses to actually transmit the information. The program is what activates and sends everything through. So if we go back to my project repository, you can see we're gonna be moving on to the source files and test benches. But I forgot one thing. Before we move over to there, we'll quickly go to the config, and the config has my constraints of my project. So the constraints that this project uses is the QSF. This contains every single file that I've created and which version. Which HDL. The nice thing about my script is I can actually mix HDL languages. So I can actually use system Verilog for one file, Verilog for another, or VHDL if I really wanted to. But I've ended up using system Verilog and Verilog. The reason I've done that is because there's some features, some ease of life features that's in system Verilog that's not in Verilog. They are basically both the same description languages, it's kind of like how you have C and C++. C++ has a lot more features. There's superset. There's only some certain features that are missing in C++. Same thing in Verilog. Um, over in over here as well, if you scroll all the way down, actually tells you the pins and the what I've renamed them to be. So pin 17, I've named them to be clock, and that is what the actual external clock on the board is connected to. I also tell it what type of like logic it uses. So some boards will use 5-volt logic, TTL. Some boards use different. So it really depends. Or like same thing with IO, like the IO standards. There's like a bunch of different types of IO. Yeah. So for basic, for the 3 pins, I've just mapped them out. Pretty simple. Pin 3, 7, and 9. LEDs, 17, clock, and 144 is button. Every other pin is up to me to decide. So I've just decided, or like pins that are that are close to each other. So that kind of quickly covers through everything that I've done. There's also like extra options that I made, like the seed, the version, project name, versioning, stuff like that. I've also created. Now, if we go back to the main project, what we can see is there's the source and the test bench. The source and test bench are the exact same file structure because hardware description languages are hierarchical. It's a hierarchy. Basically, there you have a top module which calls everything else, and that so I've taken that a similar approach to that. So if we go to my terminal and quickly use the tree command for the source and the tree for the test bench, what we can see is that for my source, in the root directory, I have my ALU, my memory, and my utility. For my test bench, exact same thing. I took the same idea to make it simple and not complex. So I have my ALU test bench, logic test bench, and memory test bench. And each one represents, it's like a perfect copy or a copy of one versus the other. Now, to continue on, since I've made it into a GitHub repo, what we can do is we can actually see some of the documentation that I've made on how I've created some of the modules. So with some of the modules, if we go to the adders and test benches, what we can see is it kind of each category has that are similar to each other has a has like some sort of similarity with it, which I explained through here, how the Boolean logic works, because for my project I've opted to use gate and the data level, and I've kind of stayed away from behavioral level because it can generate a lot of bugs that are really hard to debug. So it kind of goes through my code. This one is on high level. If we go to adders, it actually shows the actual circuit I've used. So if we go down here, we can see that the circuit that I've used over here, which is the same from the unit fundamentals of hardware design, and I've kind of explained it through here. Even though the code over here looks pretty complex with indexing and the connects, it's pretty simple. I've kind of mapped it out over here with the image, basically. Whoop. Which mapped it out here. So like W connect 0 is the XOR right after the A and B, and so on and so forth. So each category has its own. So if we go back to the arithmetic and go to the multiplier, you're gonna see somewhat of a similar format of like explaining my code, how I want to go through all of that and develop it, and kind of like my explanation for it. The reports is going to be very similar to the documentation on here that I'm going to be submitting later. Okay, so now that I've showed you kind of a quick overview of my project, I'm going to quickly go to my source files, and if I go ls, so the arithmetic logic unit is the category that contains all the arithmetic operations, all the logic operations, and everything in between. If we go into the arithmetic and we press tree, what we can see is I've defined the adders and that is a whole category in its own, because an adder can be a subtractor, and I've also made a dedicated subtractor, which can be used, which the same logic can be used to actually inverse it and becomes an adder as well. That I just did that for the fun of it. And there's also logic where I've made the C star logic of bitwise AND or not XOR, and I've also made a comparator. Every single one of those are what's it called, a combinational logic circuit. So there's no clocks required for any of these modules. As soon as you put the data in, all you have to wait for is the propagation delay, which is very low, unless for the multiplier, which has a lot of gate designs, but it shouldn't be that much, so it would handle quite a bit. Now, if I go back one and go to memory, in my memory is any circuit that can hold a state. So that's kind of how I've defined it. So in my memory, I have my buffers. So the buffers can't really hold a state, but it controls the output. So it takes in two inputs and an output. The output is going to be X or undefined. I'm going to be calling it X. The two inputs is the actual data, and the enable. When the enable is 1, the data flows through. When it's 0, it's undefined. The output is undefined. So the reason for that is to actually allow the bus to be used by multiple modules without worrying about what's it called, having mixed signals, you could say. So with all of those, like you can see that I've made a buffer, a register. Then the root of the directory is both of them combined, buffer and register. Of the instruction register and the output registers, they're very similar. There's very fine, minute differences where behavior change, where I needed behavior differences between one another. Now with my counters, it's basically a D flip flop with a bunch of half adders to create a counter, which is like the standard way of doing it. And then with D flip flops, I've made a bunch of the little different ones. So you have your D flip flop, which is your takes in the clock, it captures a signal, and on the next rising edge, it just turns it off. The T flip flop is very similar. All of these have similar attributes, just slightly different behaviors. Now my memory management unit, that's kind of like it's not really a memory management unit, it just holds the address, but it's related to it, so that's why my Mars are in here. The reason I have a byte and a 6 bits is because the first time I created my CPU, I realized that byte is not enough, so I needed 2 more bits. That is to hold the instructions and the extra stuff. The RAM is just a for loop that instantiates a bunch of registers and uses the multiplexers to actually select which one, and a decoder to get the data out. My ROM is what has my control unit and my the actual data to program the FPGA. So if we go to my ROM real quick, so if we go CD to ROM, we go NVIM the control unit, you can see that I've defined a bunch of macros saying which bits corresponds to which ones. So so each of these bits will have a certain like control flow to it. So these will actually control like the enable load, execute, like all of these for each and every individual unit. The way I've done it is first always make sure it's 0, and then I've made oh no, first when the clear is pressed, it's all 0. At the begins, if it's not a clear, that means I got new data in. What it does is it does a state machine. It's like a state machine where it checks each case, and based on the case, it would give a certain different output. So what I've also made sure is to make sure all of them are 0s, and then based on the case, only the ones I need are turned on. So that's kind of like how my ROM works. It's unlike the example that that Logisim gives us, where it's an inbuilt function. It's slightly different, but overall in a high level view, they work the same. If we go to the 6-bit, one, the exact same thing is made. The only difference is this is my actual program, which calculates the factorial up to the number 8. I've Originally I did have a jump instruction. Like I had a bunch of extra instructions, but they were a little bit buggy, so I've just opted to just running them one after another rather than using like a for loop style assembly program. If we go, let's go back. All right, if we go to the utility, this has everything else. Like if I want to talk to one component to another, like translations, etc. So this has my multiplexer, my decoders. My multiplexer has a bunch of different modules, so like your byte, nibble, word, etc. My decoders is basically it's the inverse of that. So like it's the inverse of the multiplexer. So it's mainly used for my RAM module, which takes in saves it to a certain location, and the decoder gets that exact location based on the select pins. My peripherals is how I've made my FPGA board communicate with the outside world. So I have two 7-segment displays, which takes in a binary input and it outputs it as a hexadecimal, and I can just remap that to the actual 7-segment display. The debounce is for the reset because I found out that the button that's on my board is a little bit low quality, because every time I press it, there's a lot of bouncing and like signals that I didn't intend for it to be captured. So that's kind of like on a high level of how my source works. If we go back and if we go to the test cases, there are 3 main ways I've done a test case, which is my arithmetic, which is in my arithmetic logic unit, specifically under my adders or multipliers. So if we go to my multiplier and then we check the multiplier itself, what we can see here is it actually what it does is there's a for loop. I multiply by certain, and then depending on the behavior that I'm expecting, I've kind of manipulated the data so I can get a wide range of it rather than testing every single one, because 16 bits takes way too long to iterate over every single value known within the like multiplying two 16 bits numbers. Same thing, because I need to do double it. I need to compute it twice, once inside the module and once using the computer itself. So that's one way that I've made some tests. Another way I've made it is using random numbers. So like, for example, for the category of some the memory units, like for example the buffers, if I go to one of the buffers, one of the buffer test cases, you can see that I've not buffer, register test cases, you can see that I've used the urandom function. The urandom function, I can give it a range between 0 and 16 bits, and I would test it because because it's just a register, it just holds a value, it doesn't actually does any computation with any useful computation with it. So all I wanted to make sure is with any random input, it can return me the same random outputs. Not random out, like any random inputs would return the same in the output from the compared to the one that's been inputted. The third way is can be seen in my D flip flops. So if we go quickly to my flip flops and then quickly go to here and then the flip flop. All right. The third way I've done it is I've grabbed every single signal and I've physically controlled every single one, because I really wanted to know the exact behavior of what is happening within the circuit, and that just ensures that my test cases covers everything that could possibly go wrong. So that's how I've done it. So it depends on the circuit itself and the category. That's how I've kind of tested it. Now when I run the test cases, what you're gonna see is a bunch of outputs. So if I go make run test benches, so you could see that it what's called running the test bench, and it would tell me if it passed or failed, and it goes through it pretty quick. The reason it goes through it pretty quick is because if I go to my top module, every single top module is being forked recursively. For in essence, every test has its own process, so it makes it run as soon as really quick, rather than it being one after another and after another. This is just so I can actually quickly um, quickly run through all the tests without needing to wait 5-10 minutes running through all of them, since I have like 100 tests to go through. Now, after the tests are ran, there's this thing called a VCD file. This VCD file that is generated from the VPP program. What this basically does is it contains the signals over time and how they change when it goes into the module and out of the module, and it saves it inside my waves /top/VCD. So if I go GTK waves and then my top module, the nice thing about it, whoop, did I not save? CD to waves. Let's go. Yeah, it is there. So GTK wave, I think, dash wave. And then the top module .vcd. There we go. All right. So we bring that. You're gonna be welcomed with a black screen. This is actually which is really good. It's like part of the feature where I can. This is my top module, and depending on which one I want to see, I can just go through the categories pretty quickly, rather than hunting down signals and trying to find each and every single one. So if I go to something like the ALU, arithmetic, and multipliers, well, I can click on the multiplier. I can see the signals that's been inputted and the wire that's been outputted. So if I click all of those, press insert, and then I zoom out a little bit, what you're going to be able to see is the different test cases. Each one of those is a different test case. So, and as I'm dragging this yellow line through it, it will tell you what was the input and what was the output. This input was first multiplied by 0, making sure that anything multiplied by 0 stays as 0, and I swap them around as well. I've also tested here is whether it swaps A and B, because with my multiplier, it's a 16/8 multiplier, not a 16/16. The reason for that is because if it's a 16/16 multiplier, the maximum output is 32 bits, which is way too big. But a 16/8 is the maximum output is pretty damn close to 16. So that's how I've kind of decided putting it about it. There's a lot of nuances of it. So if we go to something else like memory module, like D flip-flops or something, flip-flops D, and then I can insert another one, and then I can actually see when it kind of ran and how it ran, basically. Oh yeah, you can see some signals over here. But depending on each, because some tests are more some tests run more checks than others. You're gonna see my multiplier has a lot of things going on here because it's doing more tests. Versus my D flip flop, where it's very few. There's a lot less test cases, so it's only running between here and here. It also helps that because they're all running at the same time, that everything's kind of compressed on the single timeline, so I don't have to keep on scrolling left and right, constantly. So the length of this is dependent on the longest test, basically. So that's my test cases, my waves, and all of that. How much time? 23 minutes. Yep, that's pretty good. All right, so that's the next step of this video is I'll be showcasing the actual board, running my CPU itself. It's computing stuff. So before that, I'll quickly show my make file. So if I go back to my root directory of my project, and I go make synthesize, synth. Yep, make it to synthesize. What it does is it goes to the binary of Quartus and it grabs the Quartus map. I've forced it to use the 64 bits to be a little bit quicker, which is good. And actually puts everything it puts the output of it in logging, in case if I want to check if for warnings or what happened, how much I've used, the report percentage, etc. And it also I've also done some other stuff to it, but I can't remember. If I go make PNR, so place and route, this takes in the information of the board exactly, like what family, what it uses, the encoding, which does basically the exact same thing. It puts it into the logging file, and all the outputs of it gets put in the generated. So if we go ls, so if we go tree in generated, alright, it's just a lot of files that's been created. So the over here is where it kind of hosts my RTL and all the like fun stuff that the synthesizer does. Now if I make bitstream, it converts the place and route into the flavor of programmer the FPGA actually uses, and what it basically just keeps on takes basic pipelining, takes in the input of one, puts it out to the other, and yeah. So, and then the very last step is to actually upload my FPGA synthesized program into the actual FPGA, which I've made it into a script, which is make program. Make program just runs all the three commands at once, and it uses the USB to communicate with the FPGA and actually program it. And then once it's done, the FPGA is actually doing stuff right now. I'll stop the screen recording and I'll switch to the switch recording to showcase what my CPU is going to be doing. Alright, so this is the second part of the actual presentation, where I'm going to show what I've made working so far. So right now, what I'm going to do is actually upload my code. So if I go here, quits, and then I do the make program like before, what this will do is it will synthesize, program, and do all of that. And it will go to right here where my FPGA is. So let me grab some light so I can actually show. Alright, so this is my FPGA. It's using this, this is my FPGA. This is using this JTAG connector. The JTAG connector connects down to my PC. Alright, and what I have here is I've made my own wiring harness to actually connect the 7-segment display. The 7-segment display is connected directly to the bus, so we can actually see the data moving through between the between the loader, the program, and when it's actually executing instructions and all of that. That is my power supply that's going to the breakout board. The breakout board is what's giving all of this power. And so what I'm going to do is right here is I'm going to press the reset switch, and I'm going to have my camera on the actual thing. It's going to the program that I have made has two modes. It has the program mode, which operates at a different clock frequency than the actual like running mode. So because I wanted the program mode to be as fast as possible, I just let it run at 50 megahertz. And because I want to see some of the numbers actually change as it goes through, that is running at like, I don't know, like 3-4 hertz. So anyway, when I press it, quickly goes through, and then now you can see the data, like going through the bus, executing the factorial program that I have made. And the last two FFs is my program sending a halt signal, so it would halt the actual it would halt the whole CPU, saying you've done your job, that's it. And now what we can see over here is the slowed down clocks running through it, which is, well, you can see. Well, if I press it again, if I just make this go a little bit quicker. There we go. So that's as quick as possible. As soon as I press the reset, oh, maybe it's too quick. Press the reset. It should show that what's it called? The speed. Oh, I'm not even showing it. Okay, let me put that here. All right. If I press the reset quickly, it should actually go. This one doesn't show the speed of how fast the clock is moving, because it's only 15 megahertz. But during the program phase, it takes in less that it does it really quick. So programs do it well, really fast, and then this step, it just executing the program, and you can see it actually do the thing. Now, do you have the status indicators? Oh, if I can show it. All right, you have the status indicators. So the status indicators will tell us if I hold the reset down, it would turn on the right pin, which is connected to the actual it would which is connected to the reset, telling it we've just pressed the reset button as just a debug pin, and then as soon as I let go, it's going to load it and it starts executing it straight away. And the actual this LED is just the clock itself going really fast, and the left one is the program the fastest clock. So like because it's operating on two different clocks. When I press it, the left one stays on, and then it quickly programs it, and then it finishes the whole program. And then you can actually just see the outputs right here, just going right, like really fast. Pretty damn cool. And you can see the actual inputs, and that's the clock. And if I zoom in on it, we can see, before if I would run it really, before if I would run it really fast, you can see the actual like the edges over here kind of like drop off, and it's kind of like the timing delay of the actual clock, and the actual you could see it kind of like round off, kind of like how the electronics like one of the electronic labs. And yeah, originally I wanted to get this board running with UART, so or have a like a running environment communicating with either this microcontroller or another FPGA here, but just didn't have time to it. But this is still a pretty good project. I stop recording.